Automated airflow regulation for residential wood stoves. The goal of this experiment was to evaluate a bellows box control system designed to maintain a stove shell temperature of 350 degrees F plus or minus 50 degrees. The logic was programmed to reduce combustion air fan signal once the stove shell exceeded 360 degrees Fahrenheit to prevent reaching the manufacturer's 475-degree safety limit. Performance analysis. Upon introduction of a 5-pound Presto log at a baseline of 300 degrees Fahrenheit, the following was observed. Thermal momentum. The stove shell peaked at 411 degrees Fahrenheit. While this is within the safe operating range, it represents a 51 degree F overshoot from the initial trigger point. Response lag. There was roughly a 20-minute delay between the fan signal reduction and the peak temperature. This confirms the iron's shell thermal mass requires proactive rather than reactive airflow adjustments. Airflow regulation. The fan signal successfully dropped from a high of 9.5 volts to a sustainment range of 2.5 to 4 volts, effectively breaking the temperature rise before it approached the critical 475 degree F limit. Emissions and opacity. Correlation with smoke opacity data confirms the efficiency of the 350 degree F target. Clean burn threshold opacity stabilized at its lowest levels, 4%, once the shell reached 300 degrees Fahrenheit. Throttling impact. Crucially, reducing the airflow at 360 degrees F did not increase smoke. The secondary combustion remained engaged, providing that the stove can be throttled to manage heat without sacrificing air quality. Future code iterations to refine the peak and keep the stove strictly under 400 degrees F. The next phase of code will lower the breaking threshold, initiate fan reduction at 310 degrees Fahrenheit to account for the 20-minute thermal lag, eliminate high voltage boosts, remove the 9.5 volt pulses once the shell reaches 300 degrees Fahrenheit, integrate stack gas indicators, utilize the faster response stack temperature as a leading indicator to trigger air reduction before the shell begins its steep climb. Many times we can't measure, and I want to stay with shell temperature.